Okay. Good evening, everyone. Now I shall be solving question number 4, 5, and 6 of today's tutorial on op amps. So just hold on a second. Yeah. Okay. So let's draw the diagram of question number 4 and then start looking into the picture. So you are given this resistance Ri, which is said to be of 1 kilo ohm, and the voltage drop across this is Vi. And then here comes the op amp. Then you have a resistance R2 connected in feedback, and especially if you see it, it's a negative feedback because the negative terminal of the input of the op amp is connected with the output. Okay, here comes the R1 resistance, and I connect this to the voltmeter. Okay, so here comes the needle. First things first, what do we need to find and what is given to us? It's mentioned that a current I, an unknown current I, flows into this circuit. Okay, and we need to measure this I via this voltmeter. So Ri is given to us, R1 is given to us. We need to find R2 so that for every change in I of 1 milliampere, let me call this output as VO. This will lead to a change in output voltage of around 10 volts. Okay, so if I increase I by 1 milliampere, the output voltage of the voltmeter will turn out to be 10 volts. So you are getting a proportional relationship between I and V, wherein the voltmeter is giving me indirect measure of the current that is entering the circuit. Now, how should we go about solving this? First of all, the biggest confusion that takes place is we need to put on a common ground. So for easiest reference, we can assume this potential to be the ground voltage, so that our potential reference VO is with respect to the ground, and rest of the points are also with respect to the ground. Okay, now we have this voltage Vi, right? This voltage Vi is over here, and note that since this is an op amp in negative feedback, we can apply the virtual short concept. So the voltage at the positive terminal V plus should be equal to the voltage at the negative terminal V minus. And what is that? And that is equal to Vi. So this point over here will also be Vi. All right. Now how do we find Vi? First of all, look at this current I. Where will it flow? First I encounter this node. Now there are two directions in which the current can bifurcate. But let's be careful that one of the golden rules of our op amp says that current cannot enter into either of the input terminals. So current over here will be 0. So what will happen? The rest of the current I will flow through this Ri resistance. So what will be Vi? Vi will be I times Ri, and let me assume that I has a unit of milliamperes, and since R1 is in kilo ohms, so I milliampere times 1 kilo ohm gives me I volts. Alright, so now we have found V plus. Vi is already equal to V plus, and so that's equal to V minus. Now how do we proceed? Now we look at this terminal. The current flowing from this node to R1 can be easily calculated. Let me denote that by I prime. So I prime will be V of I upon R1 because the other terminal is at ground. So that's once again I volts by 1 kilo ohm, and that's I milliampere. Alright, so once again let's apply the golden rule. Since this terminal is connected to the negative input we cannot of the op-amp, we cannot have any current flowing into it, so this I prime will directly flow in over here. Okay, and we have this potential Vi, and where is it flowing from? It is flowing from the output, which is going into the voltmeter. So this VO has the current I prime flowing into the R2 resistance and then feeding into Vi. Okay, so what can we write from the KVL? I can write VO minus I prime R2 equals Vi. Alright, so VO minus what's I prime? I prime is I times R2 is equal to Vi, and what's Vi? Vi is I. VO can be written as I into R2 plus 1. Okay, so you see that VO is proportional to VO I is proportional to VO or vice versa. And what have we been told? We have been told that for a change delta I equals to 1 milliampere, we have a corresponding change of delta V equals how much? 10 volts. Delta VO in actually. So now we take this equation star and let's change it by a small amount, a deviation. Okay, so we can write delta VO equals delta I times R2 plus 1. It's simply differential calculus. You are differentiating it. You are let's say you have a quantity y equal to mx, you change y by a small amount delta y, and that corresponds to a change delta x. Y plus delta y equals to m times x plus delta x, and based on this you can easily write delta y equals to m times delta x. It's very simple. So what are the values provided? Delta V is a volts of 10 volts and delta is corresponding to 1 milliampere times R2 plus 1. Note that this has a unit of kilo ohms. So R2 plus 1 turns out to be 10 kilo ohms, and hence my R2 turns out to be 9 kilo ohms. Okay, now let's dive into question number 5. So we first draw the circuit diagram. We have a 2 milliampere current source which feeds into the negative input terminal of the op-amp. Then the positive input terminal is directly grounded, and then you have the feedback loop connecting the negative terminal to the output via a 2 kilo ohm resistance. But we should be careful because in between we have a 1 kilo ohm resistance, and then we have a 2 kilo ohm resistor. Now it's mentioned that there's a current I flowing outside the op-amp. So how do we get to solve this? what is the current through 1 kilo ohm resistor. So we once again apply the golden principles. What's that? Since we have a negative feedback, and why do we have a negative feedback? The negative terminal of the input of the op amp is connected to the output via an element. So there's the feedback coming into the picture. Okay, so now we have V plus equal to V minus, and because it's grounded, that's equal to 0 volt. We have this happening because of the virtual short concept, and that holds only when negative feedback takes place. This is a very important condition to remember, because when we don't have negative feedback, this condition won't hold true. Okay, so in that case, the 2 milliampere current flows into at this node, and here we apply the other golden rule that current can never enter into the input terminals of the op amp. So the 2 milliampere flows down from here. We have this V minus, and we need this output voltage V out. So what can we write? And the current flowing across this 2 kilo ohm resistor is 2 milliamps. The same current is flowing over here. So you can write V minus 2 milliamperes into 2 kilo ohms equals to V out. V minus is 0 and this is 4 volts. So our output voltage turns out to be minus 4 volts. Now we analyze these special sections carefully. I shall draw this portion once again for your convenience. You have the op amp in this picture. You have the 1 kilo ohm resistor, and now what is the potential at the output? It's minus 4 volt, and over here you have a 2 kilo ohm resistor and the ground. Now let's assume the currents. Now let's look at the currents flowing into this. The current over here is assumed to be I. This current has already been calculated to be 2 milliamperes via the golden rule, and let us find this current I prime. As you can see, I prime flows from minus 4 volt to 0 volt based on the direction that I have shown over here, and the resistance through which it flows is 2 kilo ohm. So it's minus 2 milliamperes. So in reality, the current flows in this direction actually. So now at this point, we are ready to apply the KCL. So what will the KCL be? The KCL will be I plus 2 plus 2, all of them in milliamperes, is equal to 0. Let me write how it's coming. Currents are entering into the node in this fashion. So you obtain I equals minus 4 milliamperes, and that's the answer. In all such questions, the most important thing to remember are the two golden rules, which if you have a very complicated circuit, don't look for inverting or non-inverting configuration, rather go for these first principles. Now let's move forward to question number 6. What does question 6 ask? We have to design an op-amp circuit which provides us the relation VO equals minus V1 plus 5V2, where the input voltages are V1 and V2 and the output voltage of the circuit should be VO. Alright, so the very moment you see some kind of a circuit like some kind of an expression like this where all of them have the same sign, then remember we have to use something called the summing amplifier. And how does it behave? Let's look at a general case. Let's say we have voltage V1 connected with the resistor R1, V2 connected with the resistor R2. It goes all the way down till Vn with the resistance Rn. Let's connect them all to a common node and then to the negative terminal of the op-amp's input. Now we apply a feedback resistor Rf across the op-amp, ground the positive end to 0, and here goes our output. So what is the expression for this? A very simple hint would be to use the superposition theorem, and without much detail, let me straightforward set the formula in front of you. It's minus of Rf upon R1 plus Rf by R1 times V1 plus Rf by R2 times V2, so on, Rf by Rn times Vn. How can you actually prove this? Well, let's consider the effect of the source V1 only. In order to do that, let's put all of them, V2, V3, everything till Vn as ground. If we do that, then if it's ground, then by concept of virtuous circuit, this is also a ground. So in other words, this entire circuit from R2 to Rn turns out to be useless. It turns out to be ground. So in effect, in entirety, you only have this circuit, and this circuit is nothing but the simple inverting amplifier where you have Rf and R1, and we know very well that the expression for such a circuit is my V0 equals minus Rf by R1 times V1, and that's due to V1 only. A similar case can be taken when V2 is being applied and rest everything from V1, V3 and Vn are being grounded. So that will be this term Rf by R2 times V2. So you can understand by superposition principle, we add up all the terms contribution from V1, V2 till Vn, and we end up getting this result. Now how many sources are we being provided? We are being provided with two sources, V1 and V2. So first things first, we draw the bare bones skeleton diagram of the op-amp circuit, R1, R2, connect them, and here we go. We are done with the initial phase of our design, and we write our equation as minus Rf upon R1 V1 plus Rf upon R2 times V2. And what's the equation that we are provided with? Minus V1 plus 5V2. Alright, so how do we solve Rf, R1 and R2, all these resistances? So we first equate term by term. Equate this with this one, equate this with this. We equate the coefficients term by term. Rf upon R1 is 1, so Rf equal to R1. Rf upon R2 equals 5, so Rf equals 5R2, or R2 equals Rf upon 5 kilo, so it's 5. Alright, so we have these two constraints with us, 1 and 2, but we have three variables, Rf, R1 and R2, so we need the third constraint. So the third constraint that's given to us is that for an maximum output voltage VO max equals 10 volts, the maximum current through the feedback resistance is 1 milliampere. So how do we look into this? We have this op amp over here, and we have this positive terminal ground. So by concept of virtual short, we can easily consider this voltage as ground. we have this RF over here, and this is our voltage VO. What are we assuming? At voltage VO equal to 10 volts, the maximum current that can be allowed is 1 milliampere. So what is the RF that should satisfy this? Very simple. Since this is at ground, RF is VO minus 0 upon IF, VO max actually. So that's 10 upon 1, 10 kilo ohms. So we have already found out our feedback resistance. So our R1 resistance is RF, as we had calculated earlier over here. RF equals to R1. Similarly, from the second equation, R2 is RF upon 5, so that's 10 upon 5 equals 2 kilo. So our final circuit will look like this. Here's V1 connected with R1 of 10 kilo ohms, V2 connected with R2 of 2 kilo ohms, joined in parallel with the op amp, and then we have a feedback resistance of 10 kilo ohm. So this is the desired output circuit that we need to consider for the given equation. Thank you.